Good day, everybody, and welcome to this information video about our new Ocean Frontier Institute project entitled Benthic Ecosystem Mapping for Sustainable Ocean Stewardship in a Shifting Ocean Climate. My name is Craig Brown. I'm an associate professor at the Department of Oceanography at Dalhousie University. I'm one of the two principal investigators leading this project, alongside my colleague Katleen, who's the other PI based at Memorial University. We'll be leading the project team over the next 4 years. Ideally, we would have been meeting face-to-face for a project kickoff meeting to introduce the project to you all, to network, and to discuss the research and collaboration activities and opportunities. Unfortunately, due to COVID-19, that's not possible, so we decided the best way to connect would be to provide this information video ahead of an online virtual meeting that is scheduled in early July. The abbreviated title of the project is Benthic Ecosystem Mapping and Engagement, or the BEcoME project. And the overarching science question that the project will address is what role benthic habitats play in controlling shifting patterns in species and biodiversity caused by changing ocean climate. Climate-induced change on the range and distribution patterns of benthic fauna are predicted to occur in many parts of the world's ocean. In the Northwest Atlantic and Canadian Arctic Gateway, benthic ecosystems are particularly vulnerable to these climate-induced pressures. However, precise predictions on how these changes will occur, or the underlying abiotic and biotic drivers of change, are mostly unknown. When faced with warming temperatures, studies have shown that many species exhibit poleward range shifts. However, the role that availability of suitable benthic habitat plays in this process are largely unknown due to a scarcity of available seafloor mapping data. We actually have better maps of the surface of the Moon and of Mars than we have of the vast majority of the ocean floor. This is a critical gap in almost every study to date examining climate impacts on benthic faunal distributions. Through a series of interconnected cross-disciplinary work packages, the BEcoME project is designed to address this knowledge gap. We've assembled a large, diverse and experienced project team, and you'll be hearing from colleagues at Dalhousie and Memorial University who are leading the various work packages in the subsequent slides. We also have researchers from other institutions around, in Canada and from around the world participating in the project, making it a truly global initiative. We're also delighted and excited to be working with our project partners, and we look forward to forging strong and productive collaborations with you all over the course of the project. As I previously mentioned, one of the major barriers to addressing this research question is a lack of seafloor mapping data. What you're seeing here is a fly-through of a digital elevation model, or DEM, of the seafloor that we have created from all publicly available bathymetry data sources in the region. You might argue that it looks like we have the area well mapped, but it really comes down to a question of whether or not this data is fit for purpose, which relates to scale and data resolution. For the vast majority of this area, the underlying bathymetric measurements from which this DEM were created are extremely sparse, sometimes a kilometre or more apart. In other areas, we have some limited coverage of high-resolution bathymetry data, but this is by no means extensive in coverage. The result is a digital elevation model where the pixel resolution is 1 kilometre in size. And while this can be useful when looking at benthic habitat features over the entire Northwest Atlantic, it may not be sufficient for helping us address more local scale questions where higher resolution data is required. Let's think about data resolution for a moment and what we mean by fit for purpose. The DEM in the last slide was at 1 kilometre pixel resolution. On land, we're able to collect high resolution data using optical satellite sensors. These use light to image the surface of the planet, and the sensor technology can collect data at meter pixel resolutions or better. Unfortunately, light does not penetrate very far into the ocean, which means that the same methods cannot be used to map the vast majority of the seabed of the global ocean. On land, we can use data from satellite technologies to generate a wide variety of thematic maps. For example, from the satellite image of Halifax, which is at approximately 1 meter pixel resolution, we could digitize to generate an interpreted map of the land cover, showing the location of streets, parks, and other visible features. Now imagine attempting to do this at 5 meter pixel resolution. or at 1 kilometer pixel resolution. Very quickly from this example, you start to recognize the limitations posed by data resolution when mapping at local spatial scales, and we face exactly the same problems when studying and mapping seafloor habitats based on the quality and the resolution of the underlying remotely sensed data sets. Thankfully, over the last 2 decades, we've seen tremendous advances in seafloor mapping technologies using underwater acoustics. Sound travels better than light through seawater, and modern acoustic remote sensing techniques, such as multi-beam echo sounders and synthetic aperture sonar systems, can map the seabed at resolutions comparable to the resolution we can map the land using satellite optical sensors. In this image, you can see the difference in resolution between the coarse 500-meter pixel resolution digital elevation model of the seafloor on the bottom left compared to a digital elevation model of the seafloor generated from data collected using high-resolution multi-beam echo sounder data on the top right. The resolution of the multi-beam reveals the detail and the complexity of the seabed that is needed to understand seafloor habitats at more localized scales, which is needed if we are to understand how species may respond to shifting ocean conditions caused by climate change. The BEcoME project will utilize a variety of different data sources over a range of spatial scales to address the overarching science question. At the scale of the Northwest Atlantic, we will utilize the existing coarse resolution data to examine and map the geomorphology and assess the broad patterns in predicted species shifts against these seafloor features. At selected case study sites at more localized scales, such as the Bay of Fundy, for example, we'll build on past projects to utilize available high-resolution multi-beam sonar data sets and downscaled oceanographic models to assess the research questions. We'll also utilize data from emerging technologies such as synthetic aperture sonar and high-resolution ground truthing techniques to test what benefits these methods can provide. A big part of the BEcoME project will also be engaging with marine stakeholders to explore how we can collect, compile, visualize, and use community-based knowledge on benthic habitats and the geographic range of species. This form of knowledge is often underutilized, but offers tremendous potential in helping us to understand shifting patterns in species and habitat availability in a changing ocean climate, and can provide a legacy of information that can stretch back way beyond what scientific records can provide. We'll explore ways in which these data sets can be combined and interpreted to generate thematic maps. Examples of such maps may include seafloor geomorphology at broad spatial scales, predicted habitat maps for particular species using species distribution modeling approaches, and underwater landscape maps, which I like to call Benthiscapes, which represent patterns in broad biophysical classes on the seafloor. In isolation or in combination, these types of thematic maps can offer decision support for ocean stewardship. And we'll be engaging with our project partners to determine which types of geospatial information and maps are of most benefit. The BEcoME project is structured as 8 interconnected cross-disciplinary work packages, shown here, falling under 5 broad themes. These range from work packages which will focus on societal engagement, research focused at both broad and fine spatial scales, and work packages testing and developing innovative tools and techniques for seafloor habitat mapping in close collaboration with our project partners. In the subsequent slides, you will hear from each of the work package leads who will provide a synopsis of the planned research.
Hello, my name is Claudio Aporta and I'm one of the... We see our working group as a knowledge mobilization exercise and in essence as the conceptualization of the decision support systems. We're going to collaborate with industry, conservation and community organizations and government agencies to understand and visualize benthic habitats in several locations in Nova Scotia. We're going to use a participatory and interdisciplinary research approach to develop these visualizations and the framework to actually integrate the knowledge, the information, and the data that is going to be gathered and produced through this research in working with indigenous communities, we are going to follow guidelines and principles that have been used and developed by different indigenous organizations in Canada and elsewhere, and also indigenous scholars. And basically, during these activities, we're going to engage with the industry partners and communities and the scientists working in the other working groups, basically to make use of the bathymetric data sets, the geomorphology maps, and seafloor imagery as generated throughout this project. So we're going to be basically reaching out to the other working groups on a regular basis. Thank you very much.
Hi, I'm Janet Stalker, the Program Director of Ocean School, and I am one of the co-leads of Work Package 1.2, together with Dr. Paul Hill, who is a geological oceanographer at Dalhousie University. I'd also like to introduce Sonia Lee, who is the lead science producer at Ocean School, as she'll also be playing a key role in this work package. To get things started, I'm going to show you a brief video that will give you an introduction to Ocean School and the type of work that we do.
Let's dive into Ocean School. Ocean School is a free online educational experience designed to help you better understand your impact on the ocean and the ocean's impact on you. Join our youth hosts as they work with inspiring scientists and experts to discover how each of us can help shape a healthy ocean. Ocean School is filled with great stories, told through immersive video and interactive experiences. Explore ecosystems and habitats, drive an underwater robot, or even dissect a virtual cod. Each piece of media is linked to a customizable activity designed to deepen learning. Are you a lifelong explorer? Just sign in and you're off to sea. Are you an educator? Start by discovering our content. Then visit the educator space, create your Ocean School class, and explore our help center. Built with inquiry in mind, Ocean School integrates with Google Classroom. Your students will navigate through the content, seeking information in order to put their learning into action. Whether you're an educator or a lifelong explorer, there's a lot to discover in Ocean School.
Ocean School is a joint initiative of the Ocean Frontier Institute, Dalhousie University, and the National Film Board of Canada. And as you just saw in the video, we use a combination of storytelling, inquiry-based learning, and cutting-edge educational technologies to transport learners to the front lines of ocean research, culture, and enterprise. All Ocean School content is available for free and is fully bilingual in English and French. And although we've designed it for grades 6 to 9 learners, it's easily adaptable for younger and older audiences, both inside and outside of the classroom. I won't go into too much more detail about Ocean School today, but I do encourage you to visit oceanschool.ca and make a free account, dive in and take a look around. I connected with Craig Brown, Paul Hill, and a few others early in the envisioning stages of the BEcoME project when we first recognized that this was a really great opportunity for collaboration. What came out of those discussions was Work Package 1.2. So in this work package, the Ocean School team will be working with BEcoME project research team and partners to create new educational content that will introduce youth to the concept of benthscapes. Our hope is to create content that can be used within Ocean School's platform, but that can also serve as a standalone resource that the research team can use in their own outreach activities. I'll pass it over now to Ocean School's lead science producer, Sonia Lee. Sonia will be spearheading Ocean School's collaborative work with the BEcoME team members and partners on the development of this new content.
Hello, my name is Sonia Lee, and I'm the science producer for this work package. The top two photos you see on this slide here are from our Healthy Habitats module, where we explore the benthic environment with the RoPost ROV in the Gulf of St. Lawrence. We even built an interactive game of the RoPost picking up creatures and specimens from the benthic habitat on the left there. We don't go into detail about why and how we study the benthos in this specific module, so I'm really excited to augment our existing content with this collaboration in this work package. In the next few weeks, Craig, Katleen, Paul, and I will do some brainstorming on some benthic concepts that we can focus on.
Hi, my name is Katleen Rabat, and I'm Assistant Professor and Canada Research Chair in Ocean Mapping in the School of Ocean Technology at the Marine. My research focuses on mapping the spatial complexity of our ocean to better understand the spatial distribution of benthic organisms and communities. I am co-leading this project with Craig and will also be leading 2 work packages. As I'm sure you are aware, individual species possess particular physiological characteristics which enable them to tolerate and strive under specific sets of environmental conditions. For example, some species tend to associate with muddy habitats, where they feed on deposit organic matter, while others need hard substrate to attach and grow. By modeling these species-environment relationships, it becomes possible to predict how marine species and ecosystem may respond to specific changes. In the North Atlantic, with increasing temperatures, poleward rain shifts are predicted for many species. But owing to the scarcity of high-resolution bathymetric datasets, the actual role of substrate availability in driving habitat distribution in areas of predicted rain shifts has not been addressed. As such, Work Package 2 will identify preferred benthic habitat characteristics for a range of benthic species of commercial and conservation importance, and build habitat suitability models depicting current spatial patterns as well as likely shifts. Through this work, we aim to deliver current habitat suitability maps for 3 to 4 key species of economic or conservation interest, as well as build predictive maps of how this might change under different climate change scenarios. As part of this work package, I look forward to forging new collaboration and discussing with you, our partners, which species might be of interest and which new approaches might be best suited to tackle this challenge. If you know anyone who's keen to start a PhD in 2021, I'm looking to recruit to join in this project.
Work Package 3, Fine Scale Mapping. Integrating fine-scale seafloor mapping into the assessment and management of benthic fisheries for environmentally conditioned advice. This work package is being led by myself, Joanna Mills-Fleming from Dalhousie University, and Jessica Samioto from Fisheries and Oceans Canada, Bedford Institute of Oceanography. Increasingly, large amounts of complex fine-scale spatial data are becoming available for use in stock assessment. For example, fine-scale bathymetry, temperature, and salinity measurements of the seafloor, as shown here for the Bay of Fundy. To help Fisheries and Oceans Canada address the demands of the new fish stock provisions of the Fisheries Act, complex spatial temporal stock assessment methods will be developed that can directly incorporate such environmental information and combine it with more traditional fisheries data to more accurately model the population dynamics of benthic species. The use of these sorts of modeling frameworks is already driving a paradigm shift in how stock status, reference points, and environmentally conditioned advice are interpreted and implemented around the world. In this work package, environmental data and data from fisheries surveys will be incorporated into state-space modeling frameworks. We have recently developed a spatial temporal stock assessment model for a scallop stock off southwest Nova Scotia. We plan to adapt this framework to apply it to the Bay of Fundy scallop stock in combination with fine-scale habitat information. Further, we plan to test how fine-scale environmental data derived from synthetic aperture sonar can be applied to improve the stock assessment processes for benthic species.
Okay, work package 4.1 is a work package dedicated to improving our ability to characterize the seafloor. And in this particular work package, that is using a technology called synthetic aperture sonar to do so. So the work package members are myself, I'm in Earth Sciences at MUN. I'm a geologist. One of the things I'm interested in is how can we characterize and identify geological processes on the seafloor. The two other main PIs in this work package are, of course, our project leaders, Katleen and Craig, who bring the sort of acoustic mapping expertise to this work package. And then we have a PhD student, Caroline Genie, who is co-supervised by Katleen and myself, and she will be doing most of the work in this package, and she's already started. So, interferometric synthetic aperture sonar, or INSAS. So this is a technology that allows us to generate acoustic images of the seafloor. So you can see a couple examples here. And also high-resolution bathymetric maps, so topography of the seafloor. So the beauty of this technique is you can get very detailed images of the seafloor. So this image on the right, you can see not only sort of man-made infrastructure, looks like a pipeline there, some debris, but also things like you can see sediment ripples there and some sort of other bulbous substrate. But this, usually you can either collect images of the seafloor or bathymetric data of the seafloor. Synthetic aperture sonar allows you to collect both at the same time, and both at quite high resolution. So this figure on the bottom left shows what typical 1 meter resolution data that you would collect from a multi-beam system on, for example, an AUV. And with the synthetic aperture sonar, we can get 25 centimeter resolution, and then that 3 centimeter, that's the acoustic image. And in this case, these are actually old Volvos that were imaged on the bottom of Halifax Harbor. The other advantage of this technique is that the swath width, which is basically the width of your data collection as you move it along the seafloor, can be up to 400 meters, which is quite a bit wider than what you typically get for collecting, for example, side scan sonar imagery. And therefore, you can basically cover a larger area in the same amount of time. This technology is not totally new, but its applications have been limited mostly to military purposes and also energy-related offshore industries, so wind energy and offshore oil and gas, pipelines, that kind of thing. There hasn't been much application for kind of scientific purposes or environmental purposes, so seafloor characterization. And so what we want to do is basically evaluate how we can use this technology for identifying things like habitat in seafloor, substrate composition, is it sediment, if so, what grain size, and then things like depositional, erosional, anthropogenic features on the seafloor, iceberg scour marks, features associated with glaciations, and destruction from deep sea fishing, any of those sorts of things. How are we going to do this? So we're teaming up with Kraken Robotics, which is a St. John's-based company that is one of the global pioneers in the development of synthetic aperture sonar. Kraken has a project with the Canada's Ocean Supercluster called Ocean Vision. And I've copied this text from the website: development of new marine technologies and products to enable an underwater robotics data acquisition and data analytics as a service business. So a 3-year project, about $26 million. And what they're doing is, part of this project is they're using the Leeway Odyssey, the ship in the lower right, and they are going out to the Grand Banks and also off the coast of Nova Scotia with their catfish vehicle, which is imaged here, and this has the synthetic aperture sonar sensor on it. It's a towed platform, and they are collecting data, and they will give us not all, but some of the data that they collect, and that'll be what we use to fulfill the tasks associated with this work package. So they were out, actually they might be out there right now collecting data. Caroline, our PhD student, was supposed to be out there with them, but because of virus-related restrictions, she wasn't able to go, but a second trip is planned for the end of August or September, and hopefully she'll be able to participate on that. And then there might be subsequent missions later on this year or maybe next year as well to collect even more data. So this is where the data is going to come for this work package. Okay, so what are our work package tasks? Number one is collect the synthetic aperture sonar data. So like I said, this is already ongoing now, and later in the summer and the fall we'll be collecting more, and then hopefully again next year there is some money in the budget for ship time, so hopefully we can put that to good use. Two, develop data processing workflow. So turning the raw data from the towed instrument into maps and images that we can use and interpret. Sounds simple, turns out it's not, and we have already started work on this to come up with a workflow to process and clean the data and display the data. Three, interpret and ground truth the SAS data. So once we have these images and these maps, we need to interpret them and turn that information into substrate types, habitats, see if we can identify different geomorphological features and processes on the seafloor. And one part of that process will be ground truthing using imaging. So probably some sort of drop camera system where we can actually visualize and image the seafloor in areas where we collected the data, so that we can associate specific features and acoustic responses in the SAS data to what we've confirmed visually as a type of substrate or some feature. Four, survey optimization. So how can we optimize the resolution of the data and the area that we cover in these surveys? So this would be things like how high should the instrument fly above the seafloor, how fast, how much overlap of our survey lines in order to produce the best possible data over the widest possible coverage area. And then finally, linking this to the other work packages is how can we use SAS data to answer questions about the seafloor environment and changes in the seafloor environment over time. So there you are, the work package 4.1 in a nutshell.
Hi, it's me again. This time I'm moving from the broad scale role of geomorphology to the acquisition of very fine scale point cloud data. Because a lot of marine bathymetry and ground truthing data are usually acquired using downlooking instrument, whether they be cameras or acoustic sonar system. And those are usually represented using the 2D rasters. However, for many habitats, there is much more complexity, and the information regarding the heterogeneity in the third dimension is underestimated. The example shown here illustrates the complex habitat formed by cold water corals growing on vertical cliffs. As one can see, a high-resolution color 3D point cloud is truly necessary to capture the full heterogeneity of this habitat. Particularly necessary now because many such species are highly vulnerable to changing ocean conditions, and we need novel tools to quantitatively monitor habitat health. So in Work Package 4.2, we will be looking at developing new approaches for the quantitative monitoring of important species such as cold water corals. To do so, we will consider new remote sensing tools such as structure from motion or a colored laser scanner, the C-Vision, developed by Kraken Robotics. A postdoctoral researcher will be joining our team and look at the use of algorithm for 3D point cloud segmentation and classification. Developing such approaches will help expedite large-scale surveys, eventually enabling survey harmonization by simplifying comparison across sites. As part of this work package, we aim to deliver high-resolution scale and georeference 3D point cloud for the baseline assessment of habitats, as well as test a range of segmentation and classification approaches for these 3D point data. With your help, we hope that this work package will significantly improve our ability to quantitatively monitor habitat health over time.
Hello everyone, it's me again, and I'll be leading Work Package 4.3 on seafloor characterization using multispectral multibeam sonar. We have a number of co-investigators on this work package, including Paul Hill and Vittorio Maselli, who are faculty members at Dalhousie. We've recruited a postdoc research fellow, Benthic, who will support this work package, along with a graduate student, Benthic, who will be starting his MSc at Dalhousie in September. Vicky Farini at Lamont Doherty Earth Observatory in the US, Jens Schneider at the University of Kiel in Germany, and Alex Bastos at the Federal University of Espírito Santo in Brazil are also investigators collaborating on this package. We also are extremely grateful for the support of our industry partners, QPS and R2 Sonic, who we are looking forward to collaborating with on this work package. Multibeam echo sounders have been around now for a few decades, but the technology has continued to improve through hardware and software innovations during this time. Traditionally, multibeam sonars operated at a single frequency or over a very narrow range of operating frequencies and were optimized for bathymetric data collection. However, scientists soon recognized that the signal intensity, which we commonly refer to as backscatter data, could be extremely valuable for characterizing seafloor properties such as substrate type and benthic habitat. In the last few years, innovations have led to the ability of some of these systems to work at multiple operating frequencies, which allows us to collect multispectral multibeam backscatter, which can offer significant benefits for characterizing and mapping seafloor habitats. The collection and post-processing of multibeam backscatter is complex. Systems are rarely calibrated for backscatter, and the changing geometry at which the acoustic signal interacts with the seafloor makes signal processing challenging to fully understand. Post-processing software packages can now generate corrected backscatter mosaics, which remove the angular changes in the acoustic intensity in order to facilitate interpretation. However, these changes by grazing angle from the nadar beams directly beneath the sonar, labeled A in the figure top left here, through to the outer beams labeled C, differ based on sediment grain size, as can be seen in the lower graph presented here, and which offer potential use for characterizing differences in seafloor habitats. The angular range response of the sonar is also influenced by the operating frequency. Although this can complicate seafloor characterization when combining data sets from data sources collected at different operating frequencies, it can also be a benefit when collecting data at multiple frequencies at the same time with the same insonification geometry. At different frequencies, the signal will penetrate into the seafloor to a different extent based on the sediment grain size. Scatter of the signal will also be affected by bottom roughness, the scale of which is also dependent on the wavelength of the sonar operating frequency. These are all complicated aspects of multispectral acoustic imaging, and a fundamental barrier to understanding these complexities is a lack of empirical field data collected under controlled experimental conditions in a variety of environmental settings. This work package will address this knowledge gap through the collection of robust empirical data sets collected under controlled experimental conditions. The R2 sonic multibeams operate by alternating frequency between successive pings. These can be unraveled using the QPS post-processing software to compare the different signals at the same insonification geometries. We'll identify and design field surveys at carefully selected sites to help unravel some of these complex acoustic sediment relationships. We'll conduct extensive ground truthing at different insonification geometries to measure sediment grain size and geotechnical properties of the seabed. We'll also measure seabed roughness at different spatial scales using underwater video methods, as well as measuring parameters of the overlying water column. This will allow comparison of backscatter intensity measurements across a multi-beam swath to be directly compared with environmental parameters that affect the acoustic scatter. Ultimately, the research will benefit how we can use these technologies for improved seafloor habitat mapping and geological characterization.
My name is Thomas Trappenberg, and I'm the lead for Work Package 5 about data analytics. I will be working very closely with Scott Lowe, who is a postdoc, a senior postdoc at Dalhousie University, and of course with the domain experts like Craig, Katleen, and Jessica, and with the backup of Deep Sense. The basic idea is straightforward. We will have hundreds and hundreds of hours of video recordings of the seafloor, and at the moment people have to go through this by hand and classify these images. Here are a few examples which Greg already provided. So this is very labor intensive, and if you really want to do this in this large scale that we are planning, we need to automate this. We are using for this a technique called deep learning. So in deep learning, this is shown here on the left, we are giving images to a neural network. So this image will turn on particular neurons and turn off other neurons, and in this way translate this to the meaning of the image. So here it's mapped to the digits 0 to 9. We do this by showing them a lot of examples of handwritten characters, and a teacher has first to classify them. So it has to say this is a 2, and if you show different digits, you have to provide the network with these labels. But from these labels, it can adjust the connections between these layers and thereby build a neural network which can later classify unseen data. So here's an example where we do this actually on a pixel basis. On the left, you see a photograph of some plants here. This is actually for weed detection, and it's hard to see these different type of crops, but on the right, it provides actually labels for each of these pixels, and you can see it can even distinguish what is here actually onion and some other weed. So this is today fairly straightforward, so we hope we can actually achieve this fairly easily, but there's much more we can do. On the right is an example where we built an autoencoder, so where we give it an image and we just want to learn to reconstruct this image. So you would say, well, what good is that? But we will do this by building a neural network which has a code layer, which has a very narrow layer, and in this way it learns what is kind of the interesting feature in these images, and by this we can already cluster data much more interesting and probably learn about particular features which we haven't probably seen before. So there are many different techniques. In particular, neural networks are also good in combining different type of data. So we want, of course, to come to the point where we translate these image data with sonar data. So these kind of acoustic data can also be processed by neural networks, and one of the things we want to do is actually translate the like sonar data to image data or vice versa. So there's a lot of things techniques we can use for data analytics. So I hope you will we can work with all of you. We want to learn what kind of data you have, how you process them, and maybe help you with understanding what kind of techniques are there to integrate this with different data, or to automate things which would otherwise take too long.
That concludes our overview of the BEcoME project. I'd like to thank you all for your attention, and we look forward to seeing you all at the virtual kickoff meeting and to a productive collaboration over the course of the project. In the meantime, if you have any questions or queries regarding the project, please don't hesitate to reach out to me or to Katleen. Many thanks.